This is Sample 6-3, Rock on a String. I'm on page 237 in your book. So we tie one end of a lightweight string of length L around a rock of mass M because, that's what you do. Hold the other end of the string in your hand and make the rock swing in a horizontal circle at a constant speed. So it probably helps to take a look at the picture in your book if you're doing this. So we're going to derive an expression for the speed at which the rock moves around the circle. Okay, so I've drawn here my little sketch. L is the length of the string. R here, little r, is going to be the radius of the circle. And if you envision the rock going around in a complete circle, that is indeed, as a side view, the radius of that circle. And the drawing in the book is maybe a little bit better. So take a look at that. I'm going to follow this up with a free body diagram. When you're doing free body diagrams of things in circular motion, it's best to also have a sketch because the diagram's different based on where the object is. So I'm trying to be very clear that the object is on the right-hand side of this circle, so the sketch helps with that. Here's the weight of the rock. The tension in the string is going to go up in that direction, okay, up and to the left. If your rock is on the left-hand side of this circle, then the tension is going to look different. So that's why it's good to be clear. One other point of clarification here is I'm going to show you the direction of acceleration is towards the center of the circle, like that. Okay, so just like we did in Unit 2, every time we have a force, free body diagram. Well, what's next? The Newton's law formula. So I'm going to start with the y side for no particular reason. Well, no, there's a reason because forces are balanced in the y direction. Everything up equals everything down. So we have the y component of the tension is equal to the gravitational force, or the weight. Now I'm going to talk components here. Since we've measured from the vertical, the y component is ft times cosine theta, and I can just write mg here. Solving for tension, I get mg over cosine theta. If you don't do that right then, it's not the end of the world. You'll do it eventually. So let's switch over to the x side. There is acceleration in the x direction, and so the sum of the forces in the x direction is equal to the mass of the rock times acceleration in the x direction. So the only thing moving that rock in the x direction is the x component of the tension. And again, since we're measuring the angle from the vertical, then the x component is ft sine theta. So I'm going to write this one more time because something very important is coming of this. Here's my net force in the x direction. Tension is keeping this rock moving in a circle, so it is a centripetal force. So I can write this ft sine theta is equal to mv squared over r. Okay, so like I'm trying, it takes a while to let this sink in, but centripetal force is not a new type of force. We've been dealing with forces keeping stuff in a circle ever since we've been dealing with forces. But what we're learning in this unit is that we have another way to calculate some needed quantities by realizing that a force is centripetal. That means it keeps something in a circle. So, excuse me, we can equate that to mv squared over r. So now I have my two Newton's law expressions here. I'm realizing that I don't really know what the radius of this circle is though. So I need to go back to my triangle. So if you look at my right triangle here, we can say that the sine of that angle theta is equal to r over L. It's the opposite side over the hypotenuse. So I can just solve for L is equal to, I can solve for r is equal to L sine theta. So that's what I'm going to use to plug into some things. So I'm sorry, I need to go to the next page. What we learned from the y direction was that ft equals mg over cosine theta. Okay, we learned that from the y direction. We don't really need another free body diagram here. Okay, what we learned from the left side is that ft sine theta equals mv squared over r. Okay, so this is what we learned from the x side of, the y side of things. This is what we learned from the x side of things. So I'm looking to see that both expressions contain the tension. We're going to go ahead and substitute for that. So I'm going to use this formula, but I'm going to substitute the ft that I got from the y formula. So my ft is mg over cosine theta. Then I have my sine theta equals mv squared over r. Now, by this time, if you're like me, you've forgotten what the heck you're solving for. Looking back to the problem, we're looking for an expression for the speed, okay? So just keep that in mind. I'm going to do one more substitution. I'm going to do mv squared over L sine theta because I just took the time to solve for what r was, so I'm going to erase this little part here. Okay, so I know you want to cancel out the sine theta. You cannot do it. It's not going to work. What you can do is on the left-hand side, realize that sine over cosine is equal to tangent. So my left-hand side becomes, mg tangent theta equals mv squared over L sine theta. You might not be surprised to find that the mass cancels out, right? And so I get v squared. I'm sorry, I'm going to come down here. V squared equals Lg tan theta sine theta, which unfortunately doesn't get any less disgusting. V is equal to the square root of L times G times sine theta times tangent theta. I switched the order of those, but that's okay. All right, so here's the expression. I know it was kind of gross, but here's what we learned from it, okay? What we learned in a problem like this, we can often solve for the tension in the rope once using the X formula, once using the Y formula, and then by substitution, come in and solve for what we need, okay? That's part one. Now, part two is the value of this expression, okay? Because as you know by now, I'm sure, the AP Physics 1 exam has a lot of questions like, how do you get the highest speed? How do you get a low speed? What happens if the length of the string increases? What happens if you're on a different planet and gravity's different? And our plug and chug, guess and check method will work, but if we learn how to derive expressions, we can look right at it. So what we can tell from this velocity depends on the length of the string and the angle, okay? Also what planet you're on, okay? You can see that if the string is long, okay, then our velocity is going to have to be greater. So think about any time you've whipped anything around in a circle. If the longer your string is, the faster you've got to get that thing going so that it'll maintain a circular motion. So that should make sense to you. Also, if that angle gets bigger, right? If I want to hold something straight down on a rock at a very, very small angle from the vertical, I don't have to spin it very hard. But if I want to get it up almost horizontal, then I need a bigger angle. So that's the value of this dreaded derive an expression, is that once you get that expression, okay, that was just math, but when you look at that expression, you can really do some physics, okay? How do I get this thing on a long string to spin at a big angle? Oh, I need a higher speed. So that's the value in this sort of question. So thanks for hanging in there. I hope that makes some sense. We're going to talk more about the factor of change method this chapter. If I change this, how does this change? That's going to help you a lot to get past the math and to really understand how the physical world works. So that's it for this one, and I'll see you next time.